after some review of statistics in section 2.1, in this new section, we're going to introduce some very famous continuous distributions and study their properties. Most of them, or even all of them, are important to us because we will see them in questions from time to time. The first one, so we have two basic distributions we already know. One of them is uniform from A to B. This is the uniform. The other one we know is normal distribution. So here, the mean is mu, the variance is sigma squared. This is a normal distribution. Of course, we don't really apply uniform or normal distribution to model the claim civility because they are really not a good candidate for claim civility. But they are somehow useful in building some more sophisticated models. That's why I put them as not exactly. So I put them as some prerequisite, okay, to say we also know these two continuous distributions. So now let's introduce the first important one. It's called exponential distribution. If a random variable x has an exponential distribution, its PDF should be given in this format. Different people or different textbooks have different notations. So please always follow the notations from this textbook. So here, this is the PDF because sometimes people use 1 over n to replace 1 over lambda to replace lambda in this definition, okay? But we don't use it. It's always lambda. In our case, it's always lambda times exponential of negative lambda x. Obviously, this must be non-negative. Here is the notation. This somehow fancy guy is not epsilon. This is the calligraphy font of E. So this is the calligraphy font of big E. E obviously stands for the exponential distribution. Once you know the PDF, I mean, they are equivalent. So you can do a quick integrate. So let's say x is positive. I integrate from 0 to x. Let's say fxv u du should give me my CDF, right? So this is a quick exercise to get the CDF. Once I know CDF, 1 minus it will give me the survival function. From here, I can get the hazard rate or hazard function if I want. Right, so they are equivalent. So 4 of them are equivalent. So all of those relations are two-way relations. From small f, I integrate to get big F. From big F, I use 1 subtracted to get survival function. From survival function, I can take the logarithm, take the derivative, and put negative. I get hazard function. Right? From hazard function, I can integrate and take exponential to get the survival. From survival, 1 minus it give me, right? So it's two-way traffic. So when we define a continuous random variable, we can pick either one of them, right? Any one of them will do. So here we pick the probability density function. You can choose CDF or survival or hazard function, any one of your preference. It's okay. So the hazard rate is lambda. This is somehow not a good thing, right? Because if you try to model the claim severity, you don't like the hazard rate to be constant. What it means by a constant hazard rate? That means if you still use the example of bulb, so which means the hazard rate is the same for a brand new bulb and a bulb that is close to its lifetime, which is not something we like, right? So another example could be our, lifetime, right? So for someone is young, like a 20 years old, you wouldn't expect that his mortality rate or the hazard rate is the same as someone who's 90 years old, right? So although exponential distribution is popular, it's probably not a fantastic choice, right? Simply because the hazard rate should be somehow an increasing function of the time or of the scale, but hardly, it's a constant. Once we do integral, we can get the expected value and the variance. Well, again, some most uh, test menus will ask you to memorize, but I would actually ask you to actually compute. Once you know how to compute, even you forget, you can easily derive, right? It's x times the density lambda e to negative x. So I leave this for you to complete because this is a standard example of integration by parts. All of you should know how to do integration by parts, right? And for this, you can try second moment first, right? Once you get second moment, you need to subtract by the square of the first moment. But somehow, it's more convenient probably to study its MGF. Let me do MGF. By the way, MGF by definition is the expected value of exponential function of tx. So it's etx times the density. So it will be, well, you can take lambda out if you want. So negative lambda minus t x dx. So obviously t has to be less than lambda. Otherwise, when you integrate, you get infinity. So if we do the antiderivative, this is exactly the result. Of course, well, if you want, you can write this if you want. From 0 to infinity. When you plug in 0 or when you take the limit of 0, this is lambda minus t times x. When you take the limit of x go to infinity, this exponential is negative infinity, so it's 0. When you plug in 0 is 1, so that is why you get this is. So from here, you can easily differentiate to get the result, right? So if you differentiate the MGF, what you will be getting? Again, it is a function of t, not lambda. So lambda is a constant. So this has to be squared. Okay, so negative 1 will cancel. So it's this way. So when I take t to be 0, it is my first moment. So it will be lambda over lambda square. So it's easily 1 over lambda. So you should get the same result from the integral. Okay, so if you want to know the second moment, you need to differentiate this function again. So when I differentiate again, I will be getting, okay, -2 will cancel the negative sign, so I will have 2 lambda divided by lambda minus t cubic. So my second moment will be this derivative evaluated at time 0, at t equals 0, so it will be 2 divided by lambda cubic, right? So I easily get the variance will be 2 divided by lambda square minus the square of 1 over lambda. So I get it 1 over lambda square. So this gives you another way to get the expected value and variance. Please complete the integral exercise, right? So the next one is more useful. It's the gamma distribution. Gamma distribution is actually includes many famous distributions, like the one we just studied. Exponential is a special case of gamma. What would be the parameter? So exponential lambda, it is the same as gamma 1 over lambda. So you can check, by the way, gamma 1 is 1, which we will see, right? If gamma 1 is 1, so there is a gang, so then you can flip it up, so it's lambda to the first, so it's lambda, okay? There's 1 minus 1, the zeroth order is 1, so this is e of negative lambda x, exactly, it's exponential. So we can see exponential is a very special case of gamma distribution. For gamma distribution, it has 2 parameters. alpha and beta. For exponential, you only have one parameter. So the more the parameters, the better the flexibility for you to fit the data. But of course, you don't want the number of parameters to be too huge, because if that's the case, estimating parameters could be a trouble when you have a lot of data. So by definition, this is the density. So it looks a little crazy, but if you know the definition of gamma function, you can actually derive this, because for anything to be a CDF, what do you need? It has to be non-negative, and the integral from negative infinity to positive infinity should be 1. In our case, we consider non-negative, so the integral should go from 0 to infinity. In general, it should start from negative infinity. So those two are the basic properties we need. As long as those two are satisfied, you have yourself a PDF. So what we can do is we start the standard definition of gamma function. This is a gamma function, okay? 2.28. Here is exactly the definition of gamma. Here we require alpha to be a real number. So here we even require to be a positive real number. By the way, gamma function is also defined for a complex number. So if you are interested, please use Wikipedia to read more information of gamma distribution and all the distributions we are about to introduce. Those pages will give you a complete history. Knowing the history of those distributions is actually fun. You know, you will learn a lot more from there. So once you have this, well, obviously for gamma distribution, you only have one parameter, alpha, right? I mean, how do you change? I mean, here the variable is y, right? You can introduce a change of variable. So let's just say this is beta x, right? Then you can get to what? Well, it's not beta x, so it's, let's put this x divided by beta. Okay, you can then you can go back to what we have. So in this case, okay, when y is 0, x is 0, beta should be positive. So when y is infinity, x is infinity. My y is x divided by beta to the alpha minus 1. So e to negative x divided by beta. So my dy will be dx divided by beta. So let's move everything. So the constant is beta to the power of alpha. So that's the denominator. So if I collect the x, I have alpha minus 1. My exponential is exponential of negative x divided by beta dx, right? So this is an alpha function, right? So on the right-hand side, my integrand is obviously greater than 0, but unfortunately, the integral is not 1. So all I need to do is to divide by it, right? So in that means 1 equals from 0 to infinity, 1 divided by gamma alpha beta to the alpha, so it's x to the alpha minus 1 e negative alpha divided by beta dx. So obviously this is positive, and the integral from 0 to infinity is 1. Check. So you have a density function. That's how you get the density of a gamma distribution, right? So like I said, if you understand the mathematics behind everything, literally there's little to nothing you need to memorize, right? But you know, if you really don't understand, well, I have to say you will need to memorize this, okay? Not for this course, but for SOA exam, because for this course you are allowed to bring in a cheat sheet or even open book for the exam, but that's not the case for SOA exam, right? So you need to memorize. We have this very, very useful formula, which you can easily prove by integration by parts, right? all you need to do is to do one step, and then you will see the result. And I already mentioned gamma 1 is 1, which you can check easily. By the way, another important result is gamma half is square root of pi. Okay, I'm not sure whether you can prove this. I leave this for you to check. At least you can get the result from Wikipedia. The hint I can give you is think of the PDF of a normal distribution. Right? For a standard normal, what is a PDF? 1 over square root of 2 pi e of negative x squared divided by 2, right? So this is the standard one, but of course it's quite far away at this stage to say what it looks like there, right? But anyway, you can use this result to prove this. What you need to know is if alpha is a positive integer, gamma of alpha is alpha minus 1 take factorial. Okay, you should know the mean and variance. You can directly calculate those two results by simply limits of x times the density, which is okay. So you can actually calculate to get the result. Please try. It will at least test your calculus ability, right? What I want to mention is it's a lot easier to calculate the moment generating function. From the moment generating function, it's very, very easy to prove those two results, right? So first, if you want to calculate the MGF, so how about we do the MGF? So again, it's the expectation of exponential tx. Okay, so I write down or I copy. So another reason why I always prove important result is because when you start writing things down, it actually helps you memorize, right? So what is the density of gamma function? So, like when I teach this course, I need to write it down many, many times. It actually helps me memorize, although I don't need to. So I would expect you to do the same. It not only helps you understand the result, it actually helps you to use the result in a much faster way. So here I have exponential, here's Ix exponential. So let's collect like terms together. Okay, how about we call this guy 1 over beta tilde. Let's call this 1 over tilde beta equals this guy. Okay, that means my beta tilde equals beta divided by 1 minus beta t. Okay, of course this has to be positive, meaning, okay, so this is positive, meaning this has to be positive. So my t should be less than 1 over beta. Okay, once that is in mind, so what I need, x, there's nothing I need to do with that. Okay, so here originally is beta to the alpha, but I want to put beta tilde to the alpha. Okay, of course, by doing that, I actually changed the value of this integral, which I don't want. So I need to times back and divide by the original one. Then there's nothing I changed. So now, okay, let me get a different color. So look at inside. This is inside. The integrand is the PDF of a new gamma distribution. It's gamma alpha beta tilde. That means the integral should be 1, right? If the integral is 1, I can directly get this result. Okay, once I have the MGF, I can simply differentiate and get the result, right? So if you are, once your calculus is at certain stage for this function, you can easily see the result, right? So when we differentiate, right, first of all, you should treat it as a negative alpha power, right? So when you differentiate, negative alpha will come out, and then you have negative beta. So negative cancel negative, you have alpha beta, and your power needs to be reduced by 1. So if you put it in the denominator, it's alpha plus 1, right? So let's take t to be 0, alpha beta, right? So I directly see the expected value is the first derivative evaluated at 0. It is alpha beta, right? So please do another, take another differentiation to get to the second moment, and then you will see the variance of this result, okay? Again, proving those will help you first understand and then memorize those results. By the way, the gamma distribution also includes like a chi-square, like Aaron distribution. Those you might know if you let's see whether I have any space. Let's put it down here. Both chi-square distribution and Aaron. So I leave this for you to check. Think this as a extra reading material. Try to search for the information of these two distributions. The next one we study is Weibull distribution. Here, for the textbook we use, the author introduces a two-family Weibull distribution. Sometimes you might even see three parameter Weibull distribution, alpha, beta, lambda. So here we only have alpha and lambda. Okay. I don't like its PDF because somehow it's complicated. So I will directly go to the CDF. Or even if you look at the survival function, okay, so this is the survival function of a Weibull distribution. What is the survival function of an exponential? So let me put a little box to show. So let's say if x follows exponential of 1 over lambda. Okay, so then my survival will be e to negative, right? By the way, that is why in many textbooks people actually use 1 over lambda as to replace our lambda. Okay, from here you can easily see the connection between Weibull distribution and the exponential distribution, right? Exponential distribution is also a special family of Weibull, right? So you can somehow see the connection between gamma and Weibull, right? They have some joint parts. They have intersection, right? Exponential is only a special member of that intersection. So I think this will actually help you understand or at least memorize the Weibull distribution, right? So this is easy, right? So you can see the difference is for the exponential term, x divided by lambda, you actually raise the power to the alpha, okay? And that is the survival function of your Weibull. So once you know the survival, 1 minus survival is obviously the CDF. Once you know CDF, you differentiate, you get to the PDF. So I wouldn't recommend you to memorize this. If you really need to memorize, try survival. Okay, from survival, you can easily go backwards to get the PDF. Okay. For the same reason, I ask you to do the proof for expected value and variance. It's actually not that terribly difficult. Well, it's not easy either. For this, what I would suggest you to do is remember we proved an important result from the previous lecture is this, right? So from here I have e to negative x divided by lambda to the alpha power. So let's remove this dx. Okay, this is not that easy to show, but obviously you can see this can be connected to gamma function, right? So if you go back to gamma function, is this, right? Here we have some power term times exponential, but here we only have exponential. But however, this is not negative y, this is negative some power. So that motivates you to do change of variable, right? So once you do a change of variable for this, okay, you will see the connection. I leave this to you to try. Again, you know, those are mathematical, you know, like a content. They will not appear in exam of this course or SOA exam. So this is definitely additional material. If you are able to prove, that means you are at a higher level of this course. The final one we introduce is Pareto. Pareto is quite famous, right? And again, you may see the definition slightly different. Here we have two parameters, alpha and gamma. This is our definition. Again, I don't want you to memorize this. What I want you to do is here. Okay, the survival function is in a power form. Okay, so this is actually a lot easier. From here, you can differentiate, put a negative sign, then you go back to the PDF. Pareto is a special case. It's very heavy-tailed. So let's see whether we have some graph. We only have the graph for Weibull. So again, I give you another exercise to draw the graph for Pareto. And especially try plotting the PDF for different values of parameters and to see how the shape of the tail will change, right? So this is one of the cases we call the heavy tail. So it has heavy tails. So heavy is a relative concept. It's compared to a normal distribution of the same mean and variance. So let's say, so let me use a different color. So obviously, let's say I have a normal distribution, okay, in this way. So let's draw it a little longer. Okay, so now I have another distribution. Right, so the tail part, okay, this solid line is on top of the dotted line. Dotted line is normal distribution, right? So it's higher, so it means heavier or fatter tails. So that's usually what we call the heavy tails. The tails is so heavy that MGF does not exist because it has so many big values with somehow non-small, you know, non-trivial probabilities. So when we take the exponential and we calculate its expected value, it blows up. You know, you get infinity. So you cannot apply the formula from MGF to differentiate to get the moments because it doesn't work. Okay, we have infinity. But that does not mean we can't calculate the expected value. So we can, let me write out this is the survival function, right? So if you choose the survival function as the integrand and integrate from 0 to infinity, you get the expected value. So from here, constant can be taken out, right? And when you differentiate negative alpha, you need to go up by 1 divided by the new power term from 0 to infinity. When you plug in infinity, it's obviously 0. When you plug in 0, what you get is alpha, gamma to the alphas. And here's gamma to the negative alpha plus 1 divided by negative. Negative becomes alpha minus 1. So here is gamma divided by alpha plus 1. So for the second moment, you know, of course, you have the density down here, right? So you can always integrate to get the second moment. It takes a little extra effort to complete. So again, I will leave that as somehow as exercise for you to try, okay? I think it's, okay, so before we end this section, I give you an interesting result. It's purely mathematical. For me, I found it to be very interesting. This table right? I mean, many study manuals will probably ask you to memorize those formulas. Try your best to understand and even try to prove all of them. And once you are able to prove them, of course, you will understand at a much better level. So the last thing I want to add is a pure mathematical result. Okay, so what it is. So assume I have a continuous random variable which follows Pareto alpha gamma distribution. Okay. Now let me define a new random variable y, which is defined as log x plus gamma divided by gamma. Okay, because x is non-negative, so this ratio is always bigger than 1. So when I take a log function, y is also bigger than 0. Okay, so for any small y bigger than 0, I'm interested in the CDF of y. So that means that is the probability that the big Y is less than small y. Okay, I know the definition of y is log x plus gamma divided by gamma less than 1. So what I do is I take exponential on both sides of the inequality. Then I will get x is less than gamma times exponential of y minus gamma. Right? Of course, I did a little more calculation to move everything to the right-hand side and leave x on the left-hand side. So now this is the CDF of x, right? I know I should integrate from 0 to the entire value. Okay, so what is the CDF? What is the PDF of my Pareto? So if you remember, it will be this. At the bottom is x plus gamma to the power of alpha plus 1. Okay, if you this is a power function, so doing integral is relatively easy. So what you get is, so here is negative alpha minus 1 plus 1, right? And then you divide by negative alpha. So you can actually cancel this alpha if you want. So in the end, what I have, when I plug in 0, it's here is negative alpha, right? So it cancels, so it's 1 minus. So the top part, with this gamma will cancel this gamma. So it's exponential will cancel. So it's nothing but negative alpha y, right? So what is this? This is exponential, right? So if you recall your definition of exponential, that means y is exponential with parameter alpha. So this is exponential distribution. So we can actually establish the connection between Pareto and exponential. Exponential and the Pareto are also connected, right? So I think it's mathematically beautiful. So that's why I present this to you. And another reason I show this is because remember in the end of last lecture, here we have somehow this formula which the textbook puts it as a theorem, meaning it's very important. But I really don't like you to memorize things from here. All you need to do is to follow what I did in this particular example. So we want to find something of y, introduce the definition, and then convert the inequality from y to x. We know the distribution of x, and then apply the PDF or apply the CDF of x to get the result you want. Eventually, that becomes something of y. That's what we are looking for. So do not apply that result or that theorem directly. I don't want you to do that. So let me finish down here, and we will continue to discuss in the next video.